Recording is on.
I was wondering actually what would happen if you could record twice.
Recording is on.
Okay, so now we got two recordings.
Yeah, double sure.
All right.
That's okay, Ken. Just in case.
Okay, it's recording.
Okay, so we got two recordings, so Ken can practice doing the recording, and then we're all good to go. Okay.
Let's just do multiple recordings just in case one dies,
Yeah, no, it makes sense. Okay, so let's get started. Excuse me. Thanks everybody for joining us tonight. Please note that all our meetings are recorded and made available to the public on our YouTube channel. By participating, it's understood that you have accepted these terms. Just a couple of notes before we get started. I guess some of you may have noticed that when you want to start a Jitsi session, or if you want to join a Jitsi session, they're now asking for a moderator. And that all happened back in August. And the reason being was, as always with these things, undesirables were starting to do naughty things, shall we say. And so Jitsi is now requiring the sign-in. As of now,
it wasn't me.
Yeah. As of now, there are only three sign-ins that they accept, and that is one from Google, Facebook, or GitHub. Those are the sign-ins that will allow you to start a Jitsi session. So practice it going forward in case you have to start one of these meetings one day. Also, I think we had some problems last week meeting with some bandwidth issues. Everybody's experiencing it. So maybe if you haven't done so already, maybe just turn down the performance on your settings, just down one notch, and you should be able to go. So tonight, we've got Dave with part one of the Miller effect. And also, I have the results of our poll, so I can discuss that a little bit at the after Dave's presentation, if there's time, of course. And we can roll the poll in the round table, but we'll worry about that later. All right, Dave, if you're ready.
Yep. Let me see if I can make this thing work. Now there's a tab here that says also share system audio. That's new.
Oh, I hadn't seen that before.
So because I got a couple of videos, or I got one video I got to show. So let's see, I may have to, I'm going to turn it on.
Okay. Well, we'll just play around and find out what happens. Yeah.
Sure. So there, you should be able to see my screen.
Yes.
Can you guys see my screen? Can you see my big giant cursor?
Yes. Yeah.
Okay, so today I want to talk about the Miller effect. I've been on a rant for the past couple of years now on MOSFETs and amplifiers because they've been challenging to me, and I've been pulling my hair out and all kinds of stuff. So I've done quite a bit of research and into MOSFET amplifiers and amplifiers in general. And there's this thing called Miller effect, which impacts a lot of amplifiers we use. So before I start, I just want to show this video here.
Well, I could go on for hours, but I'd probably start to bore you. You know, I really couldn't blame Elaine. I wanted a career. When they built those roads, they had no thought of drainage in mind. So we had to take a special Jeep up to the main road. In fact, we were lucky to even get a Jeep since just the day before, only one we had broke down. Bad accident.
Did you guys see that okay?
Yeah.
Yeah.
Go on.
Okay, so what I want to cover off today, I'm going to talk a little bit about MOSFET construction, some observations, what happens with MOSFETs, and stuff which I've talked about before. I'm just going to regurgitate some of the stuff I've been talking about before. But the only thing new is I'm going to get into a little bit of what the Miller effect is, the Miller capacitance theorem, and some calculations to demonstrate what it is and back that up with LT-SPICE simulations. So that's what I want to cover off today. And then in the next presentation, there's going to be a part 2. I'll be talking about how to address the Miller effect, because there's ways, done a lot of research and some simulations in terms of what you can do to neutralize the Miller effect in amplifiers. And then subsequent, there's going to be a 4th presentation, which on feedback amplifiers and how they actually work, because I've found that not a lot of people understand, or maybe they understand it, but there's a lack of documentation of what a feedback amplifier, how it actually works, what it's doing, how does it impact gain, how does it impact, input output impedance. So I'll be talking about that in a subsequent talk. So as always with all my talks, I'm no expert in this. I like to talk. Give me a mic and a soapbox, and I'll talk for hours. So it's just what I've surmised going through and reading texts and looking at equations and doing all kinds of stuff. So just be aware I'm no expert, and take what I say with a grain of salt. Okay, and here's some places where I got information for this talk to put this together. And when I learned about Miller effect and amplifiers, our good friend W2AEW, he's got a really good video on cascode amplifiers and the Miller effect. There's Dr. K. He's a professor. I can't remember what university, but he's got some good content. And Professor Fiora, he's also got some good stuff, more so around derivation of the Miller effect. And in the past, on Matteo Aboy's channel, I've referred to this woman as Matteo Aboy's grad student, and she's not. She's actually a full professor. Her name's actually Dr. Christina Crespo. So she's a full professor, and she teaches advanced, a second year electronics engineering at, I guess, a university somewhere in Spain. So her videos are phenomenal, very good. So this, I guess for everyone here, this is more so for entertainment, because what I'm going to be showing you is not something as an amateur radio operator you're going to be using day to day. So it may be a little bit painful for you to watch, but it's not something you do, because typically the majority of us take a circuit, build it, solder it together. We have a kit, build it together, and all the background analysis and all the stuff is done for us in the background. So, this is more of a, I guess, like an entertainment, bit of an entertainment for you. But I try to document things more so if you, in the future, you need to understand this, you could come back to this video, you look at it, and it may make more sense to you. So next couple of slides is from my presentation I did on Down the Rabbit Hole. It just talks about a MOSFET construction. And I think you guys could see this video, right?
Yeah, we can.
So basically a MOSFET is, you've got this substrate, and you put a layer of oxide and a metal conductor top of it, and you dope two areas, the drain and the source. And if you just take a look at this, you've got a metal layer, an oxide, which is a insulator. Then you've got this P substrate. So that's basically a capacitor, right? And so what happens if you apply a voltage across this drain and source? You've got a layer of positive charge ions here. Typically people call them holes. As you apply a positive voltage here, you attract electrons here and you push away the holes. And what starts to happen as you increase the voltage, you start to create a channel. And this channel starts to form. And eventually, once the voltage is strong enough and a channel is formed right across, you have electrons flowing. And the MOSFET is now turned on, and electrons are starting to flow. So that's basically all a MOSFET is. So if you take a look at this, you've got it just riddled with capacitors. You've got this layer and insulation between that forms a capacitor. You got a capacitor here. It's just riddled. If you take a look at this and you break it down, you can see there are all kinds of capacitors here. A MOSFET is just one big giant capacitor. Same thing with a BJT transistor. And you could take all these capacitors. These are all intrinsic. They are all inside the MOSFET. They're all built in. There's nothing you could do about it. It's got these MOSFETs inside. So if you take your MOSFET, it's as if these capacitors are added. There's a capacitor that goes from the gate to the drain. This is inside the MOSFET. Then there's a capacitor between the gate and the source, and a capacitor between the drain and the source. And all that arises from all these capacitors here. So one of the things I did was I said, you know what? With all these capacitors, let me just try and model this in LT Spice, and let me see if I could get the same behavior as a MOSFET gets. And so I built this little model here as a whim, using the parameters here. And I've got another subsequent slide, I show how these parameters here, this is from the data sheet of the IRF 510, and how those translates to these capacitors, to CGD, CGS, because it's not CGS. Here it's CISS, COSS, CRSS. Then you've got some other lead values here, which I put into the model. And if you look at this video here by Christina Crespo, she gives the equations for how this, and you'll find this in a lot of other places. I'm just quoting her as a source, but you could solve these. And figure out what CGD, CDS, and CGS is just from some simple manipulation here. And I actually did it. You could see the little calculations here that I did. So then what I did, I took a IRF 510, I took my model, and I looked at the voltage here coming in, or the impedance. I think I looked at the impedance coming in, seen from this point here, and seen from this point here, and I compared the two. So here is for the actual IRF 510. This is the impedance coming in, looking into the IRF 510, and this is my model here. And if you look at it, the impedance looking in at low frequencies, there's a little bit of a difference between it. It's about like 30 ohms or so difference, but down at higher frequencies, they're bang on. They completely match. So up until this point, what I saw was, hey, this MOSFET tends to short out at high frequencies. It's got something to do with these capacitors inside of them, and they're causing, the input impedance to be very small at high frequencies. And this is where this guy John Miller comes in, and the Miller effect comes in. Now, as I go forward and I talk, you'll periodically see me referring to an AC model. And this is very common in transistor analysis. If you have a complex waveform, sometimes it's easier to break it down into an AC component and the DC component. If you add these two together, you get the complex waveform. So that way it might be easier to deal with the DC component and deal with the AC component. With amplifiers, it's the same thing. And there are literally hundreds and hundreds of videos. If you just go on YouTube and you search for AC small signal model for a transistor, you'll get a ton of videos of people showing you how this all works. I'm not going to go into this in detail, but you'll see me talking about the AC small signal model. And just basically the DC model, it's all about the cap. So the DC models, these high value capacitors are DC blockers. So you remove anything downstream and upstream of this cap, and the circuit you're left with, you do a DC analysis. With the AC analysis, you short all caps because the AC sees this cap as a short circuit. You short all voltage sources to ground, and you do your analysis. So, for example, here's RB. It's connected to a voltage source. It's grounded. And same thing with RD and same thing with RL. They're all grounded. And the MOSFET, you replace it with a current source. And it's a current source that the current is driven by this parameter transconductance value. And the voltage delivered to the gate drives the current here. So if we take our model of a MOSFET with all these intrinsic capacitors, and we look at the AC model of this, which is a current that is driven by the gate voltage. So once the gate voltage goes past the threshold voltage, a current starts to flow. If the gate voltage is below the threshold voltage, there's no current. There's a little bit of leakage current, but for intensive purposes, there's no current flowing. So this equation here, I talk a little bit about it in my talk I did on the transistor tracer. And I show in the transistor tracer how it calculates GM and calculates all these other parameters. So if you want a little bit more information on that, go back to my transistor tracer video. But so anyway, so if the gate voltage here is 0, there's no voltage here, well then the voltage of this capacitor, and again, these capacitors are inside the MOSFET, they're intrinsic capacitors. So if there's 0 voltage here, there's 0 voltage here, this is grounded, so the voltage across this capacitor is 0. However, if this voltage here is 0, there's no current flowing here, and from the DC, the source, your supply, to across this resistor, since there's no current, the voltage is the same. So VDS is VDC, and this capacitor is now charged to VDC. Whatever, if this is 12 volts or 13 volts, this capacitor is charged to 13 volts. So now as you increase the voltage here and you get past the threshold voltage, well, this current starts to flow through this MOSFET. Current starts to flow, and as current starts to flow here, there's a voltage drop, so VDS now decreases. Now, as VDS decreases, this capacitor now discharges because it's got a lower voltage. So this capacitor now starts to discharge, and as IDS increases, and this voltage here gets lower and lower, and eventually it'll get to 0 or close to 0. This capacitor now is completely discharged. And what happens now, as you increase the gate voltage, this capacitor starts to charge now relative to gate. So what we're seeing here is this capacitor charges as the gate voltage comes on initially when there's below the threshold voltage. All current flows into this capacitor. It starts to charge. Then once a current starts flowing across here and this voltage starts to drop, this capacitor starts to discharge. And once it gets to 0 or close to 0, this capacitor now starts to charge relative to the gate. So all this charging and discharging causes the MOSFET a delay in terms of how quickly the MOSFET can turn on. And this is critical for when a MOSFET's acting as a switch, for example, in a buck converter or a buck boost converter. And if you look at the IRF 510, you can see here's what I was talking about, the capacitance of the the MOSFET, but here it gives you the charges to charge these capacitors. So here's the charge to charge the gate, the source capacitor. It takes 2.3 nanocoulombs to charge it, and the gate to drain takes 3.8, and the total charge. Now there are other capacitors in there, so obviously these two numbers don't add up to that, but the total charge needed to turn this MOSFET on is 8.3 nanocoulombs. Now keep in mind, 1 coulomb moving in 1 second is 1 amp. This is 8.3 nanocoulombs. It's a tiny amount of charge that's flowing. So one interesting thing is this kind of caught me a little bit by surprise. If you look at your scope probes, this is what my scope probe appears to be inside the scope. So it's 1 mega ohm in parallel with 18 picofarads. So once you connect this to your circuit, potentially it's 1 mega ohm, which is really high impedance, but it's 18 picofarads. So if you've got 15 picofarads between your gate to drain capacitor, you're adding a potentially 18 picofarads. So you're potentially doubling this. So depending where you put these probes, you could have a dire effect on that MOSFET, how that MOSFET turns on. So it's something to be aware of, is that your probes could impact the MOSFET behavior. So this is a little bit of an egghead chart. It shows a lot of things, a little bit confusing, but basically showing several things. It's this line here showing the gate voltage as a function of time. This orange line here is showing the current that's flowing through the MOSFET as a function of time. And the purple line here is showing the voltage here at the drain as a function of time.
Hey.
And they've also put, yeah.
Did you want to take questions as we go along?
No, at the end.
At the end, okay.
Yeah, okay. So, yeah, because this is going to be long enough. If I pause with questions, we're going to go for over an hour and a half.
Yeah, okay, no problem.
So as you turn on the MOSFET, you apply a voltage to the gate. Okay, remember I said this capacitor starts to charge. Your gate to drain capacitor is charged relative to your source supply voltage. So during this portion, as you slowly increase the gate voltage, you're charging CGS. You're charging this capacitor. Once you hit the threshold voltage, at which point the current starts flowing down here, you'll see current here now increasing. The MOSFET now is turning on, and there's current flowing down here, and VD is starting to come down. VD is dropping because there's a current across this resistor, and there's a voltage drop. Now, the interesting thing is once you get to a certain point, okay, the gate voltage is basically, it's locked in. It's held constant, and that's from this capacitor discharging, and that's called the Miller plateau. And once that capacitor is discharged, then it begins to recharge again, and both capacitors continue to charge, and that's this point here. So right at the end of the Miller plateau, that's when you've reached the maximum current coming through here. You've hit the maximum, and your drain voltage is at the lowest point. You see right at that point there. So right at that point, your CGD and CGS is almost fully charged. Okay. Now, if we take a 2N7000 and we simulate this in LT Spice, and we put a really fast pulse across the MOSFET here, and we take a look at what's happening, this is over like 7 nanoseconds. So you can see right here, here's the CGS charging. here's the Miller plateau, right? And here's the capacitors continuing to charge, and right at that point, the MOSFET's turned on. So it takes, like of the order about 4 or 5 nanoseconds for that capacitor to turn on, which is a long time. So in summary, so far, what we found is that I talked about, I observed that these MOSFETs tend to short out at high frequencies. The impedance tends to go down. It's got something to do with the capacitors. I've now showed that the time for the MOSFET to turn on is dependent on these capacitors charging, this CGS and CGD charging. And in some data sheets, they actually give you how much current is needed, how much charge is needed for those capacitors to charge. So let's start talking about the Miller effect, capacitance, and theorem. I found this to be very confusing because a lot of people use these terms interchangeable. Anytime you Google Miller, you'll find them using these terms interchangeable, and it's very, very confusing. To me, what the Miller effect is, it's what's happening. It's the effect of the capacitors have on the overall transistor. And here, they talk about it's forming a low pass filter on that signal coming in because of the capacitors, those intrinsic capacitors. The Miller capacitance and theorem is telling you how to mathematically deal with that capacitance and how to figure out what the bandwidth of that transistor or that MOSFET is going to be. So the Miller theorem, this is what the Miller theorem basically says. If you have any inverting amplifier, it's got a gain of, say, minus A. It's an inverting amp, so it's got a negative gain, right? If you have a capacitor across the input to the output, it's the same from a mathematical perspective for analyzing, the bandwidth. It's the same as taking that capacitor and putting it across the input to ground and across the output to ground and increasing the value by A. So for example, if this gain was, say, -9, and this capacity was 1 picofarad, so the equivalent Miller capacitor you're going to put here is 1 times 9 plus 1, 10. So 10 times 1 is 10. So 1 microfarad equals 10 microfarads across here. So you get a multiplication based on gain. The gain is the absolute value. So even though it's negative here, you're using the absolute value of it. You're not plugging in -9 in here or -A. You're taking the absolute value. And the same thing happens with just about any impedance. For example, you put a resistor across the input to the output, it's the same thing. You put the resistor to ground on either side. However, with an impedance, not a capacitor, the value of that impedance decreases by the gain. Okay, so again, if you've got a 100 ohm resistor here, you've got a 9, a gain of -9. So you've got 100 divided by 9 plus 1 is 10. So you've got a 10 ohm resistor here. So you'll have a 100 ohm resistor here. This will be a 10 ohm resistor here. And same thing at the outputs. In the case of the capacitor, the output gets increased slightly. A plus 1 over A is pretty much A. So it increases slightly. So if this is 1, it may be 1.1 picofarads. Same thing with the impedance here. It decreases by a value of A over A plus 1, which is basically A. So if this is, say, 100 ohms, this might be 98 ohms or 99 ohms, something like that. So reason I showed you that is if you look at the MOSFET here and you look at a transistor, again, these are the intrinsic capacitors. For a common source amplifier, this is your input, this is your output. That capacitor is going from your input to your output, and it has to be millerized. That's why the bandwidth drops so fast, is because this capacitor gets multiplied by the gain and it gets shorted to ground. Same thing with the transistor. This capacitor with a common emitter amplifier, where the output is at the, what's this, the collector, that's the emitter, right? So the collector is the output and the base is your input. The capacitor is going from the input to the output of your amplifier. That capacitor needs to be millerized. So, okay, let's do some calculations here. Let's put this into action and let's see what actually happens. So let's take a 3904 and let's just, this is a common emitter amplifier. So, and let's just model it in LT Spice, and let's use a low frequency sweep so that the Miller capacitance is not a factor here. The frequency is too low for the Miller capacitance to be an issue. So if we model this and we take a standard model you get from an AC analysis, and I've showed what the model predicts here. It predicts, based on all these values, a gain of 5.2 and an input impedance seen at Vin here of 5.8K. And if you look from LT Spice, we get 5.1. It's basically the same. We get 5.1 gain, and we've got 5.78. It's pretty close. You get, so this model, this AC model analysis is pretty good. So the way I arrived at that, the first thing you do is, I'm not going to spend a lot of time doing this because this is where I'll bore you guys and put you guys to sleep. But basically, the first thing you do, you ground all DC sources because we're doing a DC analysis. So this gets grounded. So this resistor gets grounded. This resistor gets grounded. And then for a BJT, we have to work out what the resistance here. There's an internal equivalent resistance called little re. You can see my calculation for little re here. And then you've got big re here. This is re coming across here. And so you have to work out what Rin is. So that's what's seen from here, what the impedance seen from here looking into this transistor is. And that's beta times this little re plus this big re. And you figure out what that is. And it's so beta times 4.91 times 200. And all these resistors are in parallel. You do a parallel, calculation of that, comes out 5817, exactly 5817. So that's where that comes in. It's documented here in case you need to do this in the future. So now let's add a feedback resistor here, and let's see the impact. So let's add a 5K resistor here. I put a 10 microfarad capacitor here. It's basically a DC blocker because I didn't want this to impact the bias of this transistor. So this has no impact. And plus, it's such a low frequency here. This is going to be like zero. It's going to have no impact whatsoever. So if we take a look at this now, and the model predicts our gain is going to be 4.3. And if I go into LT Spice, I get 3.9, which is pretty close. And the Zin seen in here is 811 ohms. I'm getting LT Spice predicts 837 ohms, which again is pretty close for a AC model. So it looks as if it's not bad. And this calculation is based on Miller. I've taken this resistor and I've millerized it and I've included. So what does that mean, millerized it? Well, here's the previous calculation I did with the two bias resistors here and the beta times Re plus big Re. And here's the millerized 5K resistor. So you take 5K, 1 plus the gain. Now the gain you use is the gain that had no feedback. So you millerize that, and again, these are all parallel resistors. You do the parallel combination, you get 811 ohms, and that's what how I arrive at that calculation there. So what about capacitance? Let's look at capacitance here now. So again, we've got this capacitor from gate to drain, which is going from input to output, and all that charging and this discharging, that's causing wonky things to happen in the MOSFET, and it's basically forming a low pass filter. And Miller said to take that capacitor and short it to the input and output, and that's going to impact your bandwidth. So if I switch to an IRF 510 here, and I take a look at the 510, and I say, okay, let me do a sweep now from 1 meg to 100 megs, and let me take a look at what the 3 dB points should be, the 3 dB cutoff. So based on the calculation of the IRF 510 datasheet, it should be 20 megahertz. But LT Spice, it says it's 1.7 megahertz, and that's the 3 dB point. So it's like, what the heck is going on? It's like, what have I done wrong here? Like, geez. And this is I've been plagued with this forever. Ever since I started looking at these MOSFETs, it's like I run into a brick wall. And it's like, what the heck's going on? And it took me a long time to figure this out. And just one day I thought, okay, what is the actual capacitance that the LT Spice is using? Is it using the datasheet MOSFET, or is it using something else? So that caused me to go down a rabbit hole. And so if you look at the datasheet is saying these are the capacitance, and based on that and that formula I've got, CGD should be 15 peaks, puffs, and CGS should be 165 picofarads. Now, are you guys still with me? You could still hear me, right?
Yeah, no problem, Dave.
Yeah.
Okay, good. Okay, so one of the things I discovered in LT Spice, as I was trying to figure out what capacitance LT Spice is using, if you do the op analysis, the operating point analysis, and you go to the log file, it tells you what capacitance it uses. There's the CGS and CGD it uses. So if you look, it's using 100 picofarads for CGS, and in the MOSFET, I was using 165, but CGD, which is the more important one, I was using 15 puffs. In LT Spice, it's using 117 picofarads, not 15. So here's the problem. And the other thing is, it's giving you the transconductance here. It's telling you the threshold voltage. It's giving you all that stuff right here from the op analysis. And again, you have to go into the error log. If you go into LT Spice, you go into the error log, you get this information. So if you take a look at the MOSFET for the IRF 510, you'll see it doesn't come out and say CISS, COSS, or CGD, CGS. It's got CGD max, CGD min. So it's got a min and a max. So LT Spice in the background is doing some kind of wonky calculation to figure out what that is. Okay, and it turns out that it's doing a whole bunch of trigonometric functions in the background. I found a paper that talks about it, and it's like, what a rabbit hole. It's like, it just boggles my mind. So you got to ask yourself, are these LT Spice models, are they really trustworthy? Can we use them? And here's a case where it's not. So I went forward and I said, okay, let me use the LT Spice values. And so I just did a mock-up of it. I did here's the Miller capacitance, the CGD capacitance that's been Millerized. Here's the CGS capacitor. It's 100 picofarads. This is 117 picofarads multiplied by the gain plus 1. And if you model this and you look at the output here, and you look at the 3 dB point of it, the 3 dB point, you see it comes out 2.01 megahertz, 2.04 megahertz. So pretty close. So, this model definitely matches what I have, my simplified AC model here. So if I use the actual IRF 510 and I do my calculations and I look at the 3 dB point, the LT Spice is saying it's supposed to be 1.7 megahertz. I'm getting 2.0 megahertz. So it's off by about 300 kilohertz, which that's not bad for a quick and dirty calculation. You're saying you're roughly the cutoff of this amplifier is going to be around 2 megahertz. That's the minus 3 dB point. And that's valuable to know. And here's the math of how I did this. Again, for your reference, basically you take, you short out the DC sources, you short out all the DC blocking capacitors. If it's a MOSFET, you remove the MOSFET. In the case of a BJT, you have to calculate that little RE and big RE and beta. For an AC model, you remove the IRF 510 because from an input perspective, this has got a very high input impedance, the MOSFET here. So you remove that MOSFET and you just plug in your capacitors, your Millerized capacitors and your bias capacitors, your source capacitors, and you do your calculation, 1 over 2 pi R in, the R, the total R, and the total Miller capacitance, and you come up with frequencies there. So you do the same thing for the input and the output. You have to look at both the input and output, and the lower is going to be your frequency, your 3 dB point. So here's the input, it's 2.047, and the output is 2.8 megahertz. So use a 2.047. Here's a 2.047. That's what I used. Okay, so this is for reference. I'm not going to go through this because I bore you guys to tears going through the calculations here, but it's here in case you ever have to go and do this. Now, this is something you kind of have to wrap your head around. It dawned on me that if you look at this MOSFET, okay, the gain of the MOSFET has not changed. The gain of the MOSFET remains the same. Okay, what's happening is because you've got this Millerized capacitor here, you've got a voltage divider. So whatever voltage you're feeding in here, okay, if there was no Miller capacitance here, low frequency, no Miller capacitance, then you get a gain of say 66, or you get a gain of 30 dB, right? But that's from here to there. This voltage compared to that voltage, right? Now if you put the capacitor here, you've got a voltage divider. All this stuff here is, an impedance that's feeding this impedance here. It's a voltage divider. I don't know if you guys could see that. So the voltage at the gate is dropped because of this, but it still gets amplified the same amount. So the net effect is the amplification from here to here drops, but the amplification from here to here is the same. I don't know if you guys could wrap your head around that. You could see that. But this is just because of the AC source we're using here. It's feeding in at this point, so we're measuring the gain relative from here to there, not from here to there. Okay, so let's do another calculation of this. Let's look at the 2N7000. So here's my simplified AC model, and I do a calculation. Same thing, I use the LT Spice model. I go to the operating parameters and I get the actual values that LT Spice says it's using. And, based on my little simple model, they match, they come out pretty good. It looks good for the minus 3 dB point. So if I use the actual 2N7000, and again, I follow it, I'm off a little bit, again, about 300 kilohertz. It should be 6, the minus 3 dB point should be 6 megahertz. Got about 5.7, so close enough. So that's pretty good. And here's the high side. So if you look at the high side, the output side, the 3 dB point for the output is 9 megahertz. So you pick the lower one, which is 5.7. So that's it. I think this is my one of my last slides. So the universe makes more sense to me now. I don't know if it makes more sense to you, but we started out the observation that, hey, these capacitors, they basically short out the ground. It's got something to do with this capacitor inside of it at high frequencies. The input impedance is like a short circuit. Then we found, these intrinsic capacitors, CGS and CGD, they charge and discharge, and they cause some wonky things. And so this guy Miller said, okay, look, those capacitors form a low-pass filter at higher frequencies. And so if you take an impedance such as a resistor and you put it across the input and output of an inverting amplifier, this only applies to an inverting amplifier. So if you put some sort of feedback impedance like a resistor between the input and output, the effect is that resistor gets reduced by the gain. So the higher you gain, the worse the effect. So if you've got a really high gain RF amplifier, you're going to get nailed by Miller. Same thing for capacitors. That intrinsic capacitor that's going from input to output, again, only applies to an inverting amplifier. Okay, the capacitance gets increased. What happens when a capacitor increases? It becomes more of a short. So, and it gets increased by the gain. So for a high gain RF amplifiers, just the intrinsic capacitors, they short out. They cause this low pass filter behavior. They basically short out. And here's why. It's because of the Miller effect. So in summary, high gain RF amplifiers are going to be problematic, period. And it's because the impedance will decrease. The input will always be shorted at higher frequencies. And that's due to the internal capacitance across the terminals. They get increased by the gain. So your 3 dB bandwidth decreases. And there's no doubt about it, especially a high gain RF amp, it's going to be problematic. The takeaway from this for me is LT Spice models. Trust but verify, especially the non-native models you get. Do not trust them. They may be telling you one thing, and you got to really look at it, because if you get a wonky result, don't think that LT Spice is right. That model you have could be wrong. So that concludes this talk. So the next talk, I'm going to talk about how we address the Miller effect. And in a subsequent talk, I am going to also talk about feedback amps, how negative feedback actually works. And I developed the equations and the models of how that feedback works. And there's a bunch of ways that you can analyze this, because I haven't seen too many people put forward an analysis of how an actual feedback amplifier works. And I found that to be quite frustrating, and I scratched my head. So I did a fair amount of work on how feedback amplifiers work. So that's going to be in an upcoming talk. So at that point, I will say this presentation is finished, and I'll open it up to questions.
Okay, thank you for that, Dave. Most interesting. I was looking forward to this, but now I'm questioning my sanity on that one. Boy, that's a lot to get your head wrapped around there, for sure. I have a few questions, but Hassan had his hand up way back when, so I'll let Hassan go first and get the tough questions over with first, Dave.
Okay, thank you. About the oscilloscope chart where you said the oscilloscope has 15 picofarads of capacitance, and that could screw up your MOSFET measurements. That
Yeah,
capacitance
depending,
is that capacitance is is sort of at the end of the cable in the oscilloscope end. There's a 1 megohm resistor or a 10 meg in between there, so it won't affect the MOSFET at all.
but I'm saying it depends where you put that probe. If you put the probe and you're measuring, you put the ground at the gate and to the drain, you're introducing stray capacitance, which is going to add to that intrinsic capacitor, which will aggravate the Miller effect. So I'm just saying you got to be careful of it. I'm not saying it's going to impact it, but you just got to be aware that that probe you're using, it's like the Heisenberg uncertainty principle. The probe you use could impact the electron or the neutron or proton you're trying to measure. So you just got to be careful that that probe is not going to impact what you're measuring. And I think if you look at Dave Jones kind of talks about that as well too.
Yeah, but that's not add to the confusion people have. That 15 picofarads is at the base of the cable. In between is a 1 or 10 meg resistor. So it has no effect whatsoever on the MOSFET. What you're saying is the probe itself, as you touch it, can introduce capacitance. That's fine, but that will be a much, much smaller amount. So it's not the
Yeah,
same thing.
but still, don't forget it gets multiplied by the gain, right? So if you got a high gain amplifier, you got a gain of say 100 or 50. If you've got even a 5 picofarad straight capacitance, that's get multiplied by the gain, right? But again, it
Oh,
depends
no,
where you put your probe.
no, it's only if Miller effect is only between gate and source or the negative terminal.
Right, right.
So the reason, like, I had another analogy for you about the Miller effect. It's like if you're catching a softball and you just put your hands out and catch it, you'll feel a thump, right? If
Yeah,
you move your hands backwards at the same speed as the ball, it's much softer. And if you move
yeah.
your hands forward, it'll be much harder. That's what it's
It's
like
gonna
when you
hurt.
have, right. So if you have, a voltage at one end of a capacitor, and the transistor is set up so that the negative of that voltage appears on the other side of the capacitor. So, your voltage at the gate, and the amplifier gives you a negative amplified voltage at the source, which is on the other end of the capacitor. The capacitor sees, a plus time, like the voltage delta across the cap is huge. It's it's not just V minus 0 at ground. It's like V, plus the gain. So that's why
Right. And
it's
so
so bad.
it's actually moving back. It's absorbing that the input, it's absorbing it, right? It's like your analogy with the baseball, you're moving your hand back, right?
Right. So if you put an arbitrary DC voltage on the other end of the cap, it has no effect. Capacitors block DC. But if you're if one side of the cap is seeing a varying voltage, and the whole purpose of your amplifier is to put like an amplified version and inverted version of that on the other side, you're going to see a much larger voltage across the cap. Therefore, the effective capacitance is kind of like the current, everything through more charge, more everything. It's as if the capacitance has been multiplied by the gain.
Yeah, I don't think this is a steady state. This is a MOSFET turn on phenomenal. So this is when the MOSFET's coming on, right? So you've got no voltage at the gate and it's coming on. That capacitor is charged to a DC voltage, right?
No, it's a steady state phenomenon, and it's for AC only. So it happens all the time. I've seen this. I've
No,
actually
but
put an LED across the capacitor, and it has a huge time constant. It decays so slowly. It's a sign that the MOSFET is boosting the capacitance.
because everything I've seen, all the videos and everything I've read, everyone says that capacitor is charged relative the DC charges that capacitor, and once that drain voltage drops, the capacitor now has to discharge, right?
No,
Because
that's the AC
if you
portion of the signal, right? That's
Yeah,
AC is
if you take a capacitor and you just apply a DC voltage to it, initially it charges, ramps up, and then no current flows through it. So steady state, you're right, no current flowing through it, but the capacitor has to charge up, right? And then
no
that
you
capacitor has to charge,
no
right?
you don't you can separate AC and DC in all this analysis. DC can be the as far as DC is concerned, the capacitor is an open circuit. As far as AC is concerned, it's a short. And in between, it's a impedance going from 0 to infinity. So you can think of it in terms of AC only. DC
Well
doesn't
then,
come into
but
this.
let me ask you this, Hassan. What causes the Miller plateau then?
The Miller plateau, um,
Yeah,
that's with frequency. Sorry, I missed that part. It's when at above a certain frequency, there's no Miller effect.
no, no. Yeah, no. So that's what they were saying. That capacitor, the gate to drain capacitor is charged. And so the Miller plateau, as that capacitor discharges, it clamps the gate voltage to a steady voltage, and that's called a Miller plateau. Once that capacitor discharges, the gate now charges it, and the gate is allowed the um, the gate voltage is allowed to rise up.
I don't know. I missed that part. I can only assume that the Miller effect reduces the gain so much that there's no more to reduce it, and so it just kind of goes
Yeah,
down.
and so that's as far as the reading of red says that Miller plateau is caused by that gate to drain capacitor clamping the gate voltage. It holds it at that voltage until the drain voltage drops sufficiently. There's enough current going through the MOSFET to make the drain voltage as close to zero as possible. Then it releases the gate, and the gate voltage is allowed to rise again. Right?
I actually don't
That's
know.
what I've read. Yeah.
I'll have to go back and listen again because I missed the part
Yeah,
about the
so
plateau.
if you yes, you're absolutely right, Hassan. That's why I said in the original I had a slide where say, okay, for steady state, if you look at the analysis, if you've got a waveform, a complex waveform, sometimes it's easy to break the DC and the AC apart and deal with them separately, just like a transistor or an amplifier. You look at the DC portion to get the operating point. Then you look at the AC portion, the AC model, and that's where you develop the gain and the input impedance and all that other fun stuff, right?
Okay, I'll have
So
to go
so I'm
back and
not
look at it.
saying I'm not saying that you have to mix AC and DC analysis. I'm just talking in terms of the Miller effect and that Miller plateau, what's causing that clamp on the gate voltage.
I should have paid more attention in that part. Sorry.
Yeah, be on time.
Yeah,
Nice.
yeah. The bottom
Yes.
line and the takeaway here, guys, is that we don't as amateur radio operators, that we build kits and we build stuff. Do we really need to know what the Miller plateau is? As I said, this is a little bit more entertainment for you guys, right? I just like to dig into the weeds of this stuff, but um, we don't really need to know this stuff. This stuff is only important if you got two different circuits you're trying to marry and it doesn't work. Well, maybe it's got something to do with that.
And that brings me to a question I have for you. Actually, I got a couple of comments, and then I'll do this question, Dave. One is the other one too is that the way you were showing there with the effect of probes and stuff. That bodes well for an active probe doing FET circuits. But
Yeah.
I also thought too, Dave, a very clever use of LT Spice in trying to sort out what was going on. But the question I have for you is when you were doing your FET amplifier experiments and stuff like that, and you were having issues there, what were you seeing then that you could now maybe attribute to the Miller effect, or could you?
Oh, just bandwidth. The amplifier, it's not a broadband amplifier. The amplifier only works on 80 or 40 meters. once you get up to 20 meters and above, you're getting a gain of like 5. You're not getting a gain of 10 or 20. You're getting a gain of 2, as you go up above 20 meters.
So anything above 20 meters, don't use a FET.
Well, don't use any transistor. This is any transistor, buddy. It's the Miller effect is any transistor you use because it's got that internal. That's why you go and you get a specialized high frequency MOSFET or a specialized high frequency transistor, and you pay the big. That's why you look at some of those RF amp MOSFETs. They're like $50, $100. That's why.
No, it's not just that. You also use a topology that doesn't suffer from the Miller effect. So common emitter suffers from Miller effect, but common base doesn't, although common base doesn't have gain. And cascode configuration doesn't suffer from the Miller effect.
Exactly.
It's two
Yes,
transistors
correct.
in parallel.
And that's what the cascode and high cas amplifiers, the hybrid cascode is what Wes Hayward has. I think it's called high cas. It's same thing. It's a common base or a common source and then a common drain, common gate. I guess amplifier,
Yes.
same thing. Exactly, Hassan. Yes, exactly.
Dave, I got a comment with the LT Spice model. I guess I gathered from then, since all the Spice models then for FETs do not have CGS and CGD are not specified specifically in there. They take a min and max in all cases, and then they do some fancy math.
I don't know. Like later on in a subsequent talk, when I talk about feedback amps and I do the analysis, I get bitten by this again.
Yeah.
I get bitten by this, and it took me literally, Peter, a month or so to figure out, it's the friggin' MOSFET model. And I spent like, Peter, I got pages and pages of like equations that I'm not exaggerating, where I'm just going through. This book is just full of equations, and I'm going, what am I doing wrong here?
Yeah.
What am I doing wrong? And eventually, everything I was doing was right. It's just the model was giving me wrong values for my calculations.
Yeah, it's too bad the models didn't have it specified that you could just go in there and appropriately, that you could just change it to suit whatever it is you have on.
And you can. I found a guy's video. I could post it. A guy, not a video. He's got a. Is it a video? Yeah, it's a video where he takes a data sheet, a MOSFET data sheet, and he said, let's develop the parameters for LT Spice. And he takes the data sheet and he reads the charts and he shows you how to generate all those parameters. So that's one of the things I was looking at doing. I've got the charts here for the 2N7000. That was one of the things I was going to go and do. And I thought, is there a way that I could go into LT Spice and just fix the values for the capacitors? And if I could just fix it, then do my calculations, I can verify that my model works. And sure enough, I did that and it works.
Yeah. Well, that's great. Does anybody else have any questions for Dave? Michael? You're muted, Mike. You're still muted, Michael.
Okay. So I guess this thinking about the Miller effect also applies to the BJT amplifier, like a common emitter amplifier, right? So this plateau thing must be there somehow as well. This plateau idea must be there. Can't hear you.
You're muted, Dave.
Dave's muted. Dave.
Yeah, any amplifier's got a negative feedback, and in particularly the common emitter and a common source amplifier, they suffer the worst. Like if you go to a common base, you don't get that. and because I think it's a current gain amplifier. And if you go to a common collector amplifier, that's got a gain of 1, or it's called emitter follower amplifier. I can't remember what it's called. It's got a gain of 1. Because it's got a gain of 1, you don't get the Miller multiplication. It's only when you
That's
get
right. Okay.
with high gain, the Miller effect rears its ugly head.
Okay.
So, you talked about the frequencies, the higher frequencies, and I was wondering if, I guess you referred to 40 and 80 meters. So I guess if you're looking at a 40 meter amplifier, the Miller effect is there, but it's not as pronounced maybe as the higher
It's
frequencies.
really small. That's
right.
right.
Does that mean that at say 20 megs, like you said, you'd have to account for that? And I guess the way you would account for this is in your mathematical in your LT Spice model for a 2N3904. The way you'd account for the Miller effect would be you'd put a capacitor, additional capacitor to ground from the base, and that would be your Miller capacitor, right?
No.
Or does the model do it automatically? Does LT Spice do it automatically?
LT Spice does that automatically. Oh, you mean, okay, yes. LT Spice does all that stuff in the background for you.
Okay, so you don't have to worry about it then. You don't have to actually insert that base to a collector capacitor into your model. It's there. It's built into the LT Spice model. Okay.
What my goal was that, okay, I built this amplifier, okay, and I built it. I want to know what the cutoff frequency is. Okay, I don't model it. Sure, you could model it in LT Spice, but we just saw that the models in LT Spice may take you down the garden path and tell you it's 20 megahertz when it should be 3 megahertz. But so what I wanted to do was to be able to have a way in a back of an envelope to be able to go in and do a calculation to say, okay, what is going to be the cutoff frequency of this amplifier that I'm building? So then all of a sudden I could see what it is, and I could determine whether I could use it on 14. Now, the good news is there are ways that you could, it's called neutralize the Miller effect. And this was something I talked with Farhan at last FDIM. I pulled him aside and we had a little conversation about this stuff, and what he said to me makes a whole lot of sense now. Once I actually went through, did the math, and he said it's basically pump a lot of current into the MOSFET. Even though everyone thinks a MOSFET is a voltage control device, it's not. It needs current because those capacitors needs to charge. So if you pump a whole shitload of current into it and you allow those capacitors to charge and discharge really fast, you reduce the Miller effect. And you do that by reducing the gate, the resistor, the current. You increase the current going into the MOSFET. If you have input impedance of 100 ohms, well, it's going to aggravate the Miller effect even more because there's less current going into the MOSFET. Whereas if you've got input impedance of 2 ohms, okay, then you've got a lot of current going in. And that's why, Peter, notice in the Phoenix amp, the Phoenix power amp, there was I think a 1 ohm resistor at the gate. There was a 1 ohm resistor at the gate of the amplifier. And that's number one for parasitic oscillations. But number two, it's saying that, okay, we're going to put a little bit of resistance, but we don't want to put too much resistance. We want that MOSFET to turn on as quick as possible.
1 ohm.
Yeah.
Very good. Okay, any other questions before we carry on? Okay, great. Thanks a lot there, Dave. Look forward for part 2 and see how we go with that. Okay.
Dave, would you be able to would you be able to post somehow the presentation you just gave so we can look at it?
Sure. All my presentations are posted on my GitHub page. I'll post the link.
Oh,
in
okay.
the URL.
I'll go look there. Thanks.
All my presentations
Yeah, they come in handy when you start doing this stuff, and go back to Dave's spot there and take a look, or on your YouTube channel as well, Dave. Okay, I just quickly go over the see if I can find it here. Our poll, if you remember the poll we posted last month. We can see that.
Yep.
Okay, so we had 16 respondents, so pretty much everybody who is a regular on these on our meetings looks like they all responded pretty much to it. And you can see there the top one is test equipment discussions and demos, followed closely with basic electronic components and circuits, and then some key CAD topics, Arduino, topics of interest discussions, and LT.
Okay, that's what I was going to ask. Okay, sorry about that.
Okay. All right, so if we do quickly, we've got about 10 minutes to go. So if we just quickly do a roundtable here, we've got about a minute each, I guess, to share our wisdom. On my bench, I've really been doing nothing. Haven't been around for about a month, really, with people visiting from overseas and then me going down south. So the only thing I've been doing really is just reading and things like that. So, which is kind of boring, I suppose. Anyway, so I'll just pass on over to the next person on my screen here, which is Dave. How's things in your shop?
Are you asking me?
Yeah.
Oh, I've just showed you what I'm doing.
Okay. Yeah. Do you have any comment on the polls?
On the polls?
Yeah.
No, not really. I think, personally, what is of interest. I think like presentations like on just how to use KiCad and how to use LT Spice and Arduino, the how-to presentations, I don't think they do much. I think showing, and I stepped out of the room, Peter, so I don't know if you said this, because I had to go start the recording again. And Ken, it didn't ask me to save the presentation, so I don't know if I saved the first presentation. I don't know if it's on my disk. But anyway, so I think like doing a topic where you use an Arduino to solve a problem, or you showed a way how you use an Arduino, or showed how you use LT Spice to solve a problem, I think that's of more interest to everyone. I don't think people really, the group really wants to see, okay, this is how you use LT Spice, or this is how you program an Arduino, or maybe what error, like you get your programming, you take someone's sketch, you're trying to load it, you get an error, this is what the error means, this is what you solve it. That's what I think would be probably of most interest, but that's my opinion.
Yeah, and that's why I'm asking during the roundtable, if you have a little bit more detail on what the poll says, it would be great. Okay, thanks, Dave. Frank, you're next up on the list. And you're still muted, Frank.
Okay.
Yep, we hear you.
All right. The Hot Water 9 that I've been working on has taken a bit of a back seat. I've got the receiver working on it, and I'm just starting the alignment of the transmitter. The receiver works, but I'm not happy with the sensitivity of it. But it took a back seat because my brother, Ken, some of you have met, he's 91, and he's decided to limit a lot of his ham radio activity. So he has given me this last weekend a trunk full and a back seat full of ham equipment. And my instructions are to keep it, get rid of it, or sell it. And any proceeds I'm supposed to use for further amateur radio equipment. So I've been testing, sorting, pricing, and doing all that stuff all week. And it looks like it's going to continue on for at least 2 months at the rate that I'm going. So I should be all ready for the spring and summer the Hamfest.
Okay.
So that's kept me. As far as the survey goes, no, I didn't have any extra comments other than the ones that I selected. So I'll turn it back to you since we're short of time.
Okay,
Yeah.
thanks, and Frank, looks good.
Yeah, Frank, one question. Hey, Frank, when you get some time, can you list what you have? Somewhere down the road.
Down the road, yes, I can. I've tried listing on Kitchener-Waterloo website a couple of things just as a test, and the results I'm getting are it's not our shipping. Shipping is a big problem. They don't want to pay for shipping, and we're too far in Amherstburg from the main run of things for people to come here. But yes, I can list it with prices and everything else.
We'll pick the stuff up on the way to 4 days in May.
Yeah.
Okay, Ken, you're up next. Did you just see what that dumb Eric posted? Okay,
Eric's
go
going
ahead,
shopping.
Put on your bench, Ken.
No, I haven't been doing much. I haven't done anything actually.
Okay.
Haven't been in the shack whatsoever for 2 or 3 months now. I've been doing more reading than anything. So that's about it.
Okay, well, reading's good, Ken. Michael, you're up next.
Yeah. Well, I was in Nova Scotia for a week, so I haven't really done much. Before that, I was doing DXing, so that's really my focus. I haven't been doing much building or anything. I was talking to Daniel and I today about V3NI. I had lunch with him today. We're talking about the automated antenna switch, which I had done a breadboard for, and we're going to change the Arduino in it to change the way it displays things. We're at the stage where we have to think about how we're going to put it in a case, and we really haven't done a lot of that yet, but that's the kind of thing we're going to be thinking about, whether we can actually get anything done between now and I think it's November 18th or whatever the meeting in November. It's doubtful we'll get much done, but I do have the presentation that I did to the Mississauga Radio Club a while ago, so I'm gonna do that one.
Okay.
So that's sort of the kind of thing I'm thinking about in terms of the poll. The thing that I sort of like is the test equipment stuff. Things like, okay, I have a spectrum analyzer. What do all the buttons do? How do I use them? Those kinds of things are the kinds of things that I'd like to know more about. And you can look at the manual and figure things out, or you can try things, I guess, is the kind of thing I'd like to do. And the basic electronic stuff, I'm interested in that as well. I'm interested in everything, but I don't really have anything to add right now other than that kind of thinking, like what do you do with the markers and how do you use them and all those kinds of things in the spectrum analyzer. That sort of thing interests me, and I'd like to learn a bit, and the way to learn is to do a presentation. So that's the sort of thing I'm thinking. Anyway, okay.
You're
that's
right.
really all.
You're right, Michael. That is the best way is to develop a presentation on a particular subject matter, and that's the best way to learn. And the finer points of our test here is you're absolutely right. And I think some of the stuff I've been looking at, I think the finer points of the spectrum analyzer will come in handy, especially since I've got it fully opened now. Okay, thanks for that, Michael.
And one other thing I can add is I lost my train of thought now. Sorry, I forget what. Oh yes, that was an excellent presentation, Dave, and the reason I asked about the presentation is I want to go through it and look at that as well as the recording and see if I can get some more knowledge about this stuff. That's what I want to do. But I thought it was really good, Dave. Thanks. Okay, that's all I have to say.
Thank you, Michael. Al, you're up next.
I'm kind of empty-handed today. Great presentation, Dave. A little bit over my head, but I learned a lot, and hopefully I'll learn some more. Not too much on the bench right now. You know, work is keeping me busy. Trying to get the house ready for winter, raking leaves, everything. So once the fall chores get done, I'll get back into the shack and start doing a few things. I've got a half a dozen kits at my disposal that I'd like to get on to. Not sure which one. I've got the age-old problem. I start a lot of things and don't necessarily finish them. So I'm going to have to go find a few of my projects that have been sitting there while I've been mulling about them and see if I can't get back onto it. The one that's been bugging me for the last couple of years is that low voltage vacuum tube DCR that I started, built. Never could make it work. So I think that's going to be the fall challenge to get back into the vacuum tube job. So that's basically it. So
Okay.
Thank you, Peter.
All right, thanks. Okay, hey, Bob, good evening. How are you today? How's your shack?
Hey, okay, all good. Nothing much. I've not been very active, but I would like to put a pitch in for spectrum analyzer presentations and how to use them in analysis and applications. And that's about it. Chasing DX, and that's about. I'm trying to working with packet radio. Tarpin, TARPN. I built quite a few. I built a couple of their TNCs, and I'm trying to get those working. But the software hasn't caught up to Raspberry Pi 4 yet.
Okay.
So back to you.
All right, thanks, Bob. Quick question, Bob, for you. Are you going to Hamcation next year?
If I can, yes. You going to be there?
Yes, I will be.
Okay, we'll meet up.
Okay, sounds good. Okay,
Okay.
thanks, Bob. Charles, good evening.
Hi, Peter. Not too much to report. I've recently moved, as I mentioned to you before, and I've been spending all of my time trying to find which box that particular tool is in before I can do any job or task. So I think I got another couple of weeks of sorting that mess out before I can actually start working on a project again. In terms of the poll, I think perhaps the categories that you put out were pretty specific, and I'm thinking that it might make more sense for them to be a bit more generic. For instance, rather than just talking about KiCad, talk about a variety of CAD tools, since not everybody uses KiCad. And again, the same with microcontrollers and microcomputers as a topic, rather than just Arduino. Again, personally, I don't use Arduino. I do a lot of stuff with Raspberry Pi, Pi Pico, PIC microcontrollers, those sorts of things. Just never got into Arduino. So I think if we could generalize things a bit more, that would be helpful.
You're right, and the problem was because the Survey Monkey, it was free, and you're not allowed to put any boxes in there that would ask like free form responses. There was all specific, so that's the problem with it. And of course, we with our groups IO, we don't have the poll function available to us because we're running on the free version. But your points are well taken. Okay, thanks for that, Charles. Dave, you had a question.
No, it's just more of a comment. I actually posted it in the chat because I see we're running out of time, Peter. Just, but Bob, it'd be interesting to learn about what Tarpin is, because I took a quick look at the website and it seems very, very interesting.
Okay.
Okay, sure thing.
Jerry.
Yeah, so great presentation, Dave. It was very interesting. In fact, I think I need to replay 2 or 3 times to refresh my knowledge. Great source of details also. Like, I think it was good that you included some of the great presentations from some of the YouTubers. In fact, I was taking a look at that quick look. I think that person also has great content in there. I think, I forgot her name, but I have looked up the video. Anyways, nothing as much has been going on my side. The last 1 month has been pretty busy at work. In fact, I missed one meeting, SOAREX in the Beanie, and the other one I could not attend due to some work at the time. So otherwise, I had to start on few kits. I've been actually, buying. Last year, I have not been able to start on any of those. And count me in when it comes to Ham Mansion at Dayton and 4 days in May.
Okay. All right. Thank you, Cherry. Hassan, you're up next.
All right, so what's been on my bench has been my bench itself. I've been fixing up the garage workbench, clearing some space because I just bought a metal lathe. So I have a new philosophy now, which is I used to just build janky benches and stuff just to minimalist, but now I realize I have to make them look pretty, otherwise I'm not motivated to actually keep them clean. And I'm going to apply that to radio. I think from now on, the next thing I build, I'm going to build the knobs first and make them really nice and beautiful. And that'll motivate me to get the rest of it done.
Well, you know what? That's an interesting point. I hadn't thought of that. You might be onto something there.
Yeah. I'll leave the good designs to Frank, and I'll just work on the good construction and stuff like that. As far as what I want to see for discussions, I think test equipment discussions are good, but one of the things I've always wanted to do is model a transistor in LT Spice and take out the model and do it as discrete components. And I got to see that today from Dave, so I can live vicariously through your work. So that's exactly what I want to see.
Okay, sounds good. Thanks, Hassan. Let's see who's up. Oh, Howard. How you doing tonight, Howard?
Oh, pretty good. Haven't been doing very much, but thanks for that talk, Dave. And I looked at that W2 AEW site when I was looking into the SDR project, trying to understand the circuit. So that's what I'm hoping to get back to do, to start that up again once the fall stuff is finished. So other than that, I haven't been doing very much. But in terms of the poll, sort of along the line of what Dave was saying, I think specific presentation or a discussion about a specific problem that someone might have, that would be interesting, in addition to a generic talk, let's say, on a spectrum analyzer, which would also be good.
Okay, great. Thanks for that, Howard. Is there any point going to you, Eric?
Sure. Yeah. I mean, I can talk about future things, but right now I have no idea what condition my bench is in. Hopefully my bench is still there, and my puppy hasn't eaten everything off of it. But looking,
Sandy stole all your stuff.
So yeah, exactly. But I think this 555 made out of discrete components would be an interesting thing to do a talk on. So once I get that back home and start picking it apart, I might just have something there, some material for an upcoming meeting.
Okay, well, that'd be really great, Eric. And I have a funny feeling the 555 was probably going to go the way of the common emitter amplifier. But hey, I'm just saying.
Are you sure?
No, but Frank, you got your hands up.
Yes. I got a question for Eric. In this group of assorted ham equipment, there is an FT101, and I know you just bought one. Did you get the manual with it?
No, I've just downloaded soft copies of it. Actually, it's a very much more complicated question. I thought you were just going to say Visa or MasterCard. But yeah, is it an FT101? Which version? Which flavor?
E. 101E.
Oh, okay. I think that's the exact one that I've got, is a single E. So, but no, you've got an actual original manual with it. Yeah?
I've got an original manual that I'm putting with it when I sell it, but
Does it have the matching amplifier?
No, there's no amplifier.
No.
Bare-
Okay.
No. I didn't know it was online, so I'm going to use the original one to go with it then, since you have got a copy.
Right. Well, just so you know, I think the one I purchased probably about a year and a half ago or so was about $200, just over $200. So.
Okay, I'm thinking in lines of about 150.
Yeah.
Sold.
Okay, Howard, do you still have your hand up, or?
Well, initially I did, but I thought Frank was looking for the manual. But just to confirm, you have a hard copy manual for it, Frank?
Yes, I do. I have a hard copy.
Okay, because I have a 101B and I also have the manual. I thought you were looking to make a photocopy of it.
No, I've got it. I just wanted to know if he wanted a photocopy.
Okay.
Okay, Dave, you got your hand up?
Yeah, I just wanted to, Frank, if you, in that trunk or that back seat full of ham gear, if you've got an 817 or 818 or any of those QRP radios, can I put dibs on it and buy it from you? Because I'd love to get hands on one of those QRP radios.
I've got a lot of QRP equipment in there because we both were QRP enthusiasts. However, 90% of it is home brewed and very, very good with all the knobs and cases and everything. It's each one is a piece of work, a piece of art. But nothing in the commercial line except there is a 10 Tech Scout, which is a 5 to 50 watt transceiver.
Yeah, one of the things, Frank, if you're looking to, part with any of that gear, why don't you put a list together of what you have and post it to the group to see if anyone would like to, purchase that stuff from you.
Yes, we talked about that a few minutes ago, and I said, yes, I will do that, but it's going to be
okay.
So, yep.
Sorry, I was in and out of the room with the recording. I must have missed that. Thanks.
Okay.
Okay. Eric, did you finish?
Yep.
Well, I guess Eric.
Sorry, I was muted. Yeah. No, I'm good. Thank you very much.
Okay.
Yep.
Okay, and last but not least is Dwayne. If you're talking, Dwayne, you're still muted.
Laying out some circuit boards, projects I want to go and build sometime, but that's nothing complete build at all, and just playing.
Well, playing's good, Dwayne. Okay. Well, I think that's about it for tonight. Thank you, everybody, for joining in. And again, thanks, Dave, for your presentation. Most enjoyable. Going to be a lot of work there to understand all that. I think, like most of us, are going to have to review that a couple of times. Okay. Thanks, everybody. Our next meeting is in a couple of weeks, November 15. It is. And I think that's the one that Michael's got the talk in there. So we'll look forward to that antenna project. And with that, I guess we'll say 7-3 and catch you guys later. Ciao.
7-3 to all.
Hey,
Bye.
Dave, send me a link to the videos, please.
Yeah, sure. No problem. I'll
All right.
post that for you tomorrow.
All right.